Yeah, hi, this is a brief introduction to the CT1, the compulsory task 1. And I'm going to, first of all, show conceptually how I'm thinking about it. And the second thing is that I'm going to go through the theory and the key equations. Then I'm going to show MATLAB script that you make some changes to. And the last thing is going to happen is that I'm going to show you the rubrics that is for the report that's going to be presented. But you'll have a couple of exercises to work with it, and you will attend a seminar on the 18th between 10 and 12 for 25 minutes. And you will also produce a report that is due during study week 4. But I will start showing conceptually how I'm thinking about this compulsory task. So what you will do is to calculate the relevant things for a wetland where a substance is degraded, a substance that comes with an inflow, it travels through the wetland, or as an engineer would say, the reactor, and leaves the wetland after a while. So there's a chemical reaction taking place, but there's also some changes in the water balance with some seepage coming in from the banks of the wetland, some rainfall, precipitation, and evaporation. And what you will do is to calculate how the flow changes through the wetland. That could decrease, be fairly constant, or decrease depending on the water balance. And the concentration of the substance coming in will probably decrease as it is degraded. So will the molar flux of substance. And since the molar flux decreases, there will be an increase in conversion along the wetland. And one important assumption is that the wetland works as a PFR, that is a plug flow reactor. So it is not mixed in this direction at all, but in this direction, it's perfectly mixed. So then I will go to the theory part and share my screen showing my pad. And I'm going to start a new pad here. So just to make a recap of the PFR reactor, the PFR is typically symbolized like this with a control volume. It has an inflow and an outflow, but we focus very much on the control volume in the middle. And we have a molar flux into the control volume. We have volume flow, and we have the concentration, maybe of A. Let's take that substance, and we have an outflow of what goes in, and the change in molar flux. We have, or may have at least, a change in flow rate, and we may have a change in concentration as well. So the mass balance is what goes in plus what is produced equals the output. And in molar terms, this is F plus R dV is the input flux, and that should balance the outflow. And so we see that these two terms, they will cancel out. But now I'm going to focus a little bit more on this, because the molar flow is composed of the product of the flow and the concentration. So this is in fact the differential of the flow times the concentration. And when you take a differential of the product, two things that may vary, we get, or it is composed of two different parts, because the molar flux can change either because the concentration changes at constant flow, or that the flow changes at constant concentration. Now that is something that we should carry with us, that the production equals the output, but the output is composed of two different parts, one related to change in concentration, one related to change in flow. So now I'm going to draw a conceptual drawing of this wetland, which is extremely simplistic, of course. But if the PFR typically is drawn as a cylinder, the wetland here is drawn by me as a slab. Rätblock in Swedish. And we have this control volume here. That is the small volume. But I'm going to put some notation here. This is dl, and this will be the height or the depth of the wetland, and this is the width of the wetland. And since we have the height and the width, dl, the small control volume can also be expressed as dv equals h times w times dl. So if we go back to our, and then here we also have the reaction. So if we go back to our mass balance, which was R dV equals Q times dC plus C times dQ, see that if we insert the volume and a kinetic expression, in this case it's given that RA equals minus K times CA, a regular first order reaction. We get minus K times CA, that is the kinetic expression, and dV equals H times W times dL, and that equals Q times dC plus C times dQ. And now we can divide both sides with dL. And then this becomes 1. And we see that we have an expression for how the concentration changes along the wetland, again, from L equals 0 to L equals L. And we have one term here that is the concentration, and we have one here that depends on the concentration. So I will just solve for the CA dL equals, and then you see there's a Q in front, and I will do like this. And then we see that we have two terms with CA, here and there. So we have, in fact, we can take that away and put in a CA instead. And since this becomes negative, if we move it to the same side as the reaction, we can even put a negative in front. So we have minus CA divided by Q, and then we have K times H times W. And then we have dQ dL. So the way to interpret this is that if we have a chemical reaction, since we have a negative sign here, the chemical reaction will tend to decrease the concentration of A in this direction. If we have an increased flow in the transport direction, it will be positive, which means that we'll have a negative influence on the concentration. So if the flow of water increases along the wetland, it will help to decrease the concentration of the pollutant. Okay, so this is one of the two key equations that you will need to set up. The other key equation is actually by looking at the water. And the processes that we have some water going in here, and then we have another flow of water leaving. But we also have a couple of processes. We have seepage of water. We have rainfall or precipitation. And we have evaporation. And in this case, the P and E have unit cubic meter per meter or square meter and hour, and S has the unit cubic meter per meter and hour. Because you know that rain falls, number of cubic meter falls on the surface, but in this case with the seepage, there's a certain number of cubic meter that enters on the side for every meter in the wetland. So if we set up a mass balance for water, we have for this dV, we have the input of water, and then we have the next term is S, and that should be multiplied with dl, since it is per unit distance that the seepage is defined. And then we have the input from the precipitation, the rainfall, and that should be multiplied with the surface, right? Number of square meter. And that is this surface here. And that is dl times the width. And then we have the output, the Q plus the dQ. And we have an output through evaporation as well. Evaporation should be multiplied with this area, which is W times dl. So the next step will be to cancel out that and that, get rid of those. And then we multiply every term with dl. Of course, these will just be ones. And we see that dq dl equals S, because the flow will increase because of the seepage. It will increase because of the precipitation, and it will decrease because of the evaporation. So here we have a nice expression of the Q, the L, which does not depend on Q itself. And of course, if we combine those two, we get minus CA divided by Q, K times H times W, and then we insert these terms, the S plus the P times W plus E times W. So here we have two coupled equations. So Q actually goes in here, which means that, yeah. So these are the two equations that we will solve. So how should these two equations be solved then? Well, they will be solved using a MATLAB script. And I'll stop sharing this and I will just show what you will do in terms of MATLAB. In previous years, there has been a lot of MATLAB programming, but we don't see that as feasible this year. So what you will do is you will take pre-prepared MATLAB scripts, small functions, and then you will add some numbers for parameters and for an expression for evaporation and the two differential equations that I just showed. And so you will prepare 3 different scripts like this, one for 4 degrees, one for 10 degrees, one for 25 degrees, with different combinations of precipitation and evaporation. And that is what you'll do. And then there will be another script that makes sort of the entire calculation for you. So you don't have to, I hope you will not be too stressed about that. So finally, I'm going to share a screen and show the rubric for the assignment for this, I think I've got it there. Okay, so rubric is, that is criteria for quality in your work. So it is, rubric will be shown on the assignment page. And just, you should have a structure with some theory and computation methods, your findings and the organization and the presentation of data and the writing style, and there will be an overall assessment. For example, if we take one example here, findings, that is the results that you come up with. They can be correct, clear, logically linked to the theory. That is really great. Or they can just be sort of well presented and discussed with relevant conclusion, or the findings may be vague or not justified or ambiguously presented. And we'll try to follow that scheme. When you've handed in your report during the study week 4, you will later get some feedback, but this time you will not get written feedback. We will give oral feedback. So we'll sit together with you in Zoom and go through your report with the things that are great and things that need some improvement. And then it will be clear afterwards what kind of revisions that we will ask for. I hope this introduction will help you to get going and have fun with CT1.